My name is Valentin Hartmann. I'm a PhD student at EPFL, and today I will present our work on how to improve the composition of differentially private mechanisms by a posteriori bounds. This is joint work with Vincent from the University of Florida, Alexander from the Institute of Software at the Chinese Academy of Sciences, and Bob from EPFL. In classic differential privacy analysis, the leakage of private information via the outputs of a mechanism is analyzed a priori, before the mechanism has produced an output. This results in a worst-case guarantee over the possible outputs of the mechanism. We have made the observation that for mechanisms from various domains, some outputs leak less information about the input database than others. We propose output differential privacy, the tool for jointly analyzing a mechanism and its output a posteriori, that is, after the mechanism has been invoked. This results in tighter privacy bounds and therefore better privacy utility trade-offs. Most likely, all of you know the definition of differential privacy, but I will repeat it here. A randomized mechanism M is epsilon delta differentially private if for all pairs of neighboring databases X and X prime, and for all subsets S of the range of the mechanism, the probability of producing the set S when invoking M on X is bounded by e to the epsilon times the probability of producing S on a database X prime plus delta. The part of this definition that we will focus on today is the universal quantifier for the sets for which the inequality holds. By requiring the inequality to hold for all possible output sets, one guarantees privacy even for the worst-case outputs. However, when applying a DP mechanism in practice, only a single output is produced, and the leakage of private information via this output might be overestimated by the standard DP guarantee. Let me give you a simple example. Consider the following mechanism. First, a coin is flipped. If the coin comes up heads, we return the value of a function f that is computed on the private database plus noise sampled from the Laplace distribution with parameter 1 over epsilon. We assume that f has sensitivity 1, and thus returning the value of f plus the Laplace noise ensures epsilon differential privacy. If the coin comes up tails, we return the fixed bottom symbol, which is independent of the database. Thus, in this case, no private information is revealed. The overall mechanism has a DP guarantee of epsilon, but obviously this is an overestimation of the true leakage in the case where the coin comes up tails. This is a toy example, but let me give you a more interesting example that we analyze in our paper. Assume a data analyst that trains a logistic regression model P in a differentially private way. After having trained the model, they compute the error that this model makes on a held-out test set. If the error is sufficiently small, the data analyst releases the model. However, if the error is too large for the intended application, there is no use in releasing the model, and the data analyst instead only releases the bottom symbol. Intuitively, and also analytically, as we show in the paper, much less information about the private database should be revealed when only the bottom symbol instead of the model parameters is released. Similar example is the proposed test release framework by Dwork and Lay. The goal is to compute a statistic f. In our paper, we analyze the case where f is the interquartile range, a measure of the spread of the data similar to the variance. The post-test release makes use of the local sensitivity of f, that is, how much the value of f changes when one changes a single record in the current database. The statistics considered in Dwork's paper have the property that if the local sensitivity is high, the statistics would not be robust enough and would thus not be interesting to release. The mechanism therefore proceeds by proposing an upper bound on the local sensitivity. It then checks in a differentially private way whether the actual local sensitivity lies below this bound. If this is the case, a noisy version of f of x is returned. Otherwise, the bottom symbol is returned, which reveals much less about the data. We've now seen 3 examples of mechanisms where the actual leakage of private information depends on the mechanism's output. But how do we make use of such an a posteriori analysis? Liegert et al. Proposed to use this insight in applications where a given utility necessarily needs to be achieved, and the privacy guarantee is secondary. In such a setting, the parameters of the DP mechanism can be chosen in such a way that the target utility is achieved, and then the achieved privacy level is computed. However, this does not yield the strong a priori bounds that we know from DP that are important in many privacy-sensitive applications. To achieve such strong privacy protection, until now we had to consent ourselves with the conservative DP bounds that do not take into account the actually produced outputs, and thus do not make use of potential privacy improvements. We show in our paper that it's possible to achieve both the strong a priori privacy protection of DP and utility improvements from analyzing the mechanism outputs. For this, we first need to formalize the examples that we have seen so far for mechanisms that exhibit different amounts of leakage for different outputs. We define the concept of output differential privacy, which applies to randomized mechanisms M. We assume that there exists a partition P of the output set of a mechanism, a value delta, and a function E that assigns an epsilon value to each set in the partition. We then say that M fulfills P E delta output differential privacy for all neighboring databases and for all output sets S, an inequality similar to that of standard DP holds. The difference is that instead of multiplying the probability on the right-hand side with e to the epsilon for some global epsilon, we split the probability up by intersecting S with the different sets in the partition P and multiply each probability by e to the corresponding epsilon. To make this more concrete, go back to our coin flip example from the beginning, where the output could either be a real number generated by the Laplace mechanism or the bottom symbol. In the former case, the leakage is epsilon, whereas in the latter case, there is no leakage of private information. As the first set of the partition of the output space, we can thus choose the real numbers, and as the second set, the set containing the bottom symbol. You can see quite easily that ODP is a refinement of DP. Any mechanism that fulfills DP also fulfills ODP, where we simply take the entire output set of the mechanism as the only set in the partition. Furthermore, any ODP mechanism fulfills DP, where epsilon is the supremum over all epsilon values for the different sets in the output partition, at least if the supremum is finite. Now that we have the definition of output differential privacy, we can use it to improve the utility of DP mechanisms. This is possible in a setting where we compose multiple mechanisms. With a total privacy budget of epsilon t and delta t, we want to spend this budget in multiple mechanism invocations. In each iteration, we choose a new ODP mechanism Mi and let it produce an output. We then check which set of the partition the produced output falls into and subtract the corresponding epsilon from the epsilon budget. In the coin flip example, we will thus subtract nothing from the epsilon budget if the output is the bottom symbol. In contrast to that, in classic DP composition, we would always subtract the epsilon corresponding to the worst case output, which is the supremum over all output-specific epsilons. This means that, depending on the outputs produced, we can save epsilon budget. This budget can either be used to invoke more mechanisms or to reduce the amount of noise required to be added in subsequently invoked mechanisms. An example for the latter application is the sparse vector technique. This DP mechanism is applied to sparse vectors that have few large entries. The mechanism works in two steps. First, it identifies the indices of the large entries in the vector. And then it releases their values with added noise. As we show in our paper, the first step that searches for the large entries leaks less private information when the number of detected large entries is smaller than in the worst case. This, in such cases, we can save privacy budget and use it for reducing the amount of noise that is added to the entries in the second step. The plot shows this for the example of a vector of length 100. You can see that for smaller numbers of large entries, the expected noise that needs to be added with an ODP analysis is substantially smaller than with a standard DP analysis. This concludes my talk. I've introduced output differential privacy, a tool for increasing the utility of privacy-preserving mechanisms without weakening the differential privacy guarantee. In this talk, I've given 3 examples of mechanisms to which our analysis tool can be applied. In our paper, you'll find one more such example. We have formally verified the correctness of our composition theorem in the proof assistant Lean. You can find this formalization and the code for generating the plots in the paper at the URL at the bottom of this slide. If you want to get in touch, You can send me an email at valentin.hartmann@epfl.ch. Finally, this has been my first submission to PETS. I would like to give a huge thanks to the anonymous reviewers and to the meta reviewer. We got very detailed and very useful feedback that helped improve our paper significantly.